The next two chapters of calculus cover concepts involving series, mostly pertaining to their convergence or divergence. We will develop a variety of tests to determine the convergence of a series. As a review, a sequence is an ordered list of numbers, but a series is a sum of numbers. An infinite series can be represented as using the summation symbol. N equals 1 is our starting point, and up to infinity. For example 1, what happens as more and more terms of a series like 2n plus 1 are added? 2n plus 1 from 0 to infinity starts off, the first term is 1, 3, 5, 7, so it looks like all odd numbers. If you added up all the odd numbers that existed up to infinity, then your sum would be infinite. When the sum of a series is infinite, then that series is said to diverge, or to be divergent. What happens as more and more terms are added to a series like 3 over 10 to the n? If I plugged in 1, our first term would be 3 over 10 to the 1. Plugging in 2, 3 over 10 to the 2. What if I wrote this as decimals? As you continue, you're going to get 0.33333 repeating, which is 1/3. So this series actually has a finite sum of 1/3. This is an example of a convergent series because it converges to 1/3, because the terms add up to be 1/3. For a geometric series, if consecutive terms in a series have a common ratio r, the series is called a geometric series. In general form, our geometric series starts at n equals 0, goes to infinity of some term times a common ratio to the power of n. If the absolute value of r is greater than or equal to 1, the geometric series diverges. But if the absolute value of r is less than 1, the geometric series converges. And you can actually find the sum of a geometric series. That would be a over 1 minus r. For the following examples, determine if these series converge or diverge, and if possible, find the sum of the series. I could rewrite this summation to be 3 times 1 over 2 all to the power of n, to make it look more like a times r to the n. This makes r, our common ratio, equal to 1/2. The absolute value of 1/2, is that less than 1? Yes. So this geometric series converges because the absolute value of the ratio is less than 1. The test we used to prove this was the geometric series test. Therefore, because this geometric series converges, we can actually find the sum by using the formula a over 1 minus r. A would be the first term, so plugging in 0 for n. If we plug in 0 for n, we're going to get 3. Therefore, our sum would be 3 over 1 minus 1/2. This series converges to a sum of 6. For number 4, r is 3/2. Is the absolute value of 3/2 less than 1? No, it is not. Therefore, this geometric series diverges. You can say it diverges by the geometric series test, or GST. In number 5, the common ratio is -1/2. Is the absolute value of -1/2 less than 1? Yes, it is. Therefore, this series converges. Again, by the geometric series test, or GST. So we can find the actual sum here. A would be our first term when we plug in 1. We get -1/2 times 4. So the sum is -2 over 1 minus -1/2. Which would make this geometric series converge to -4/3. Find the fraction form of the repeating decimal 0.08 using a geometric series. Remember in the very first example when we rewrote 3 over 10 as 0.3 and 3 over 100 as 0.03 and so on? We're going to do the same thing for this. 0.08 repeating is 08080808. Continuing, obviously, repeating. So this could be rewritten as 0.08 plus 0.0008 plus 0.000008, and so on. To me, it's much easier to figure out the ratio when it's in fractional form, but you may be able to see it now. Our first term is 8 over 100. The next one is 8 over 10,000. The next one is 8 over 1 million. So the common ratio, or what we're multiplying each time in between, would be 1 over 100. That makes r equal to 1 over 100. And a, our first term, is 0.08, or 8 over 100. To write this as a fraction, I'm going to use that sum formula that I had. The sum of a geometric series is equal to a over 1 minus r. This reduces to be 8 over 99. So if you wanted to write the decimal 0.08 repeating as a fraction, that would be 8 over 99. In general, the convergence of a series is less simple than the convergence of a sequence. For example, the sequence a sub n equals 1 plus 1 over n converges because the limit as n approaches infinity of the sequence is 1. So this sequence converges to 1. However, the corresponding series 1 over 1 plus n does not converge. A series cannot converge unless the terms approach a limit of 0. That makes for a very useful series test, only for divergence, but extremely useful. This is called the nth term test. If the limit of a sub n, the corresponding sequence, is not equal to 0, then the sum of the series diverges. This test is inconclusive, though, if the limit of the corresponding sequence is 0, then we must use another test to determine if it truly converges. To use the nth term test, we'll take the limit of the corresponding sequence as n approaches infinity. This is equivalent to terms of highest degree. In this case, it would be the factorial. I can take 1/2 out of my limit. 1/2 times the limit as n approaches infinity of 1 would be 1/2 times 1, which is 1/2. Guess what? The limit of the corresponding sequence is not 0. Therefore, the corresponding series diverges. How do you know it diverges? We used the nth term test. You could also call that NTT. The n is usually lowercase and the t's are capitalized.